This documentary was made for a simple purpose: to help you fall asleep peacefully while quietly filling your mind with the stories of history. No effort required. Just listen and let the ancient world do the rest. Close your eyes for a moment and imagine the Earth before humans, before mammals, before dinosaurs, before almost everything you know about life on this planet had yet arrived. 350 million years ago, the world looked nothing like it does today. The continents were in different places. The oceans were in different shapes. The sky above held more oxygen than it does now, and the land, vast, wet, unimaginably ancient, was covered in forests. Not forests like any that exist today. Forests so dense, so enormous, so unlike anything in the modern world that if you were somehow transported back to stand at their edge, you would not immediately recognize what you were looking at. Trees that grew to 60 meters tall without a single branch until their very top. Ferns the size of houses. Mosses thick enough to swallow a person. And living within all of it, creatures that evolution has never repeated. This was the Carboniferous period, named for the vast deposits of carbon, coal, that it left beneath the surface of the Earth. Coal that humanity would dig up 300 million years later and burn to power the Industrial Revolution. Coal that heated homes and drove engines and built the modern world. The Carboniferous built our civilization, long before our civilization existed. Tonight we go back, all the way back, to the world that became our world. Let the ancient Earth breathe around you and rest. To understand the Carboniferous, we must first understand where it sits in the vast sweep of Earth's history. The Earth is approximately 4.5 billion years old. If you compress that entire history into a single calendar year, with January 1st being the formation of the planet and December 31st being today, the Carboniferous period would begin around the 6th of December. Humans would not appear until the final minutes of December 31st. Everything we call history, every civilization, every war, every discovery, every story we have ever told, would occupy less than the last 15 seconds of that year. The Carboniferous began approximately 358 million years ago and ended approximately 298 million years ago. 60 million years, a span of time so vast that the entire existence of our species, from the first anatomically modern humans to today, would fit inside it over 200 times. It followed a period called the Devonian, the age of fishes, when the seas were dominated by extraordinary marine life and the first tentative experiments with land-based existence were just beginning. And it preceded the Permian, a period that ended in the greatest mass extinction in Earth's history, when over 90% of all species on the planet were wiped out. The Carboniferous sits between these two chapters of Earth's story as a period of extraordinary biological abundance. Life had conquered the land. The seas were full. The air was rich. And the conditions on Earth combined in a way that produced something that would never quite happen again. But what were those conditions? The first thing to understand is where the land was. In the Carboniferous, the continents were not where they are today. The great supercontinent of Pangaea was in the process of assembling. The land masses that would one day become Europe, North America, Asia, and the southern continents slowly grinding together through the unstoppable mechanism of plate tectonics. Much of what is today, North America and Europe sat near the equator, warm, wet, bathed in tropical rainfall, exactly the conditions that the great forests needed. The Carboniferous is divided into two sub-periods. The Mississippian, 358 to 323 million years ago, and the Pennsylvanian, 323 to 298 million years ago. The Mississippian was dominated by shallow warm seas covering much of the land. The Pennsylvanian was the age of the great coal swamp forests. The climate of the Carboniferous was warmer than today on average, but not uniformly so. There were glacial periods during the later Carboniferous as the supercontinent assembled and ocean circulation patterns changed. The Earth was experimenting with the climate systems that would eventually produce the world we know. The seas were warm and shallow over vast areas of the continents. Coral reefs flourished. Enormous schools of ancient fish moved through crystal-clear tropical waters. And on the edges, where the sea met the land, in the vast delta systems and coastal swamps, something extraordinary was happening. The trees were growing, and they were growing like nothing that had grown before. The stage was set, warm, wet, ancient beyond imagination, and into this world the forests came, not slowly, not tentatively, with an explosion of biological creativity that covered the land in green from equator to pole. What those forests looked like is one of the most extraordinary stories in the history of life on Earth. Stand at the edge of a Carboniferous forest and try to understand what you are seeing. The first thing you notice is the scale. The trees are not like any trees you have ever seen. They do not look like oaks or pines or palms or any recognizable modern species. They look like something from a dream or a nightmare, depending on your relationship with the unfamiliar. The dominant trees of the Carboniferous coal swamps were called lepidodendron, the scale trees. They grew to heights of 40 to 50 meters, as tall as a 15-story building. Their trunks were smooth and covered in a distinctive diamond-shaped pattern of bark scars where their leaves had once attached and fallen away as the tree grew upward. No branches until the very crown, just a single smooth column of ancient wood, rising into the sky and then exploding into a canopy of long, narrow leaves at the top. They did not grow slowly. Lepidodendron grew with remarkable speed by the standards of trees, reaching their full height in a matter of years rather than decades. They were monocarpic, meaning they reproduced only once, at the end of their lives, releasing enormous quantities of spores before dying. An entire generation of lepidodendron would grow, reach their full enormous height, reproduce, and die, creating vast quantities of dead organic material that would fall into the swamps and begin the slow process of becoming coal. Alongside the lepidodendron grew sigillaria, similar in form but slightly different in detail, their bark marked with vertical ridges and oval scars, and rising between and among them, the giant horsetails, calamites, ancient relatives of the small horsetail plants you might find today in a damp garden, but grown to the scale of trees. 15 meters tall, their jointed, segmented stems creating a distinctive architectural regularity in the forest understory, and covering every surface below, the tree ferns. Enormous ferns with fronds stretching meters in every direction, filling every gap in the canopy with dense green growth, creating a layered world of vegetation so thick that the forest floor was permanently in deep shadow, a green twilight world where the only light came filtered through, layer upon layer of ancient leaves. The forest floor itself was extraordinary, thick with mosses and liverworts, ancient plants whose relatives are among the oldest land plants on Earth, covered with fallen trunks in every stage of decomposition, threaded through with shallow water channels connecting the swamps and lakes that dotted the forest landscape. Here is the detail about Carboniferous forests that changes everything. The bacteria and fungi that decompose dead wood in modern forests had not yet fully evolved during much of the Carboniferous period. Dead trees fell into the swamps and simply did not rot. They accumulated, layer upon layer, century upon century, millennium upon millennium. This is why the Carboniferous produced such extraordinary deposits of coal, not because there was more plant life than other periods, but because the dead plant life could not be broken down and recycled. It was preserved, compressed, transformed over millions of years into the coal seams that humanity would discover 300 million years later. The dead trees of the Carboniferous forests became the fuel of the Industrial Revolution. The ancient forests that fell into ancient swamps 300 million years ago heated the homes of Victorian London, powered the locomotives of the American West, and drove the factories that built the modern world. We have been burning Carboniferous trees for 200 years, and we are only now beginning to understand what that means. The forests were extraordinary, but a forest without animals is only half a world, and the Carboniferous was full of animals. Creatures that evolution experimented with during this period of high oxygen and abundant food. Creatures that have no equivalent anywhere in the modern world. What walked, crawled, swam, and flew through those ancient forests was unlike anything alive today. The forests of the Carboniferous were not empty. They were alive with creatures, but creatures so different from anything in the modern world that naming them feels almost inadequate. These were the experimental forms of early animal life. Evolution was still working out what a land animal could be, what shapes were possible, what sizes, what strategies for survival, and it was trying everything. The first thing to understand about Carboniferous animal life is that the age of reptiles, the dinosaurs, the great lizards, the dominant terrestrial vertebrates of the Mesozoic era, had not yet arrived. We were in a different chapter entirely. The vertebrates on land in the Carboniferous were the amphibians and the very earliest reptiles. Creatures in the process of making the transition from water to land complete, or creatures that had just completed it. The amphibians of the Carboniferous were extraordinary animals. Eriops, one of the larger Carboniferous amphibians, was a heavily built creature, roughly 2 meters long, with a massive skull, powerful jaws, and a body plan that sat somewhere between a large salamander and a crocodile. It was one of the apex predators of the swamp edges. It hunted fish in the shallow waters and took anything small enough to fit in its enormous mouth on the land. Ophiderpaton and its relatives were elongated, snake-like amphibians that moved through the dense undergrowth of the forest floor, limbless or nearly so, hunting invertebrates through the leaf litter and shallow water of the swamps. And then there was Hylonomus. Hylonomus is remarkable, not for its size. It was small, perhaps 20 centimeters long, looking somewhat like a modern lizard, but for what it represents in the history of life on Earth. Hylonomus is among the earliest known reptiles, a creature whose eggs could be laid on dry land without drying out, whose skin retained moisture more effectively than an amphibian, whose entire biology was adapted for a life that did not depend on returning to the water to reproduce. A tiny, unremarkable-looking animal that represented one of the most significant evolutionary transitions in the history of vertebrate life. From Hylonomus and its relatives would eventually come, given enough millions of years, the dinosaurs, the crocodilians, the birds, the mammals. Every land vertebrate alive today traces its lineage back through the reptile line that began in the Carboniferous forests. We are the children of Hylonomus, in a very real sense. But the vertebrates were not the most numerous or the most spectacular animals in the Carboniferous world. That distinction belonged to the invertebrates, and specifically to the arthropods. The Carboniferous was the age of the arthropod. Insects, arachnids, myriapods, the centipedes and millipedes. These were the dominant animal forms of the terrestrial Carboniferous world, and they achieved sizes and forms that the modern world has never seen repeated. Arthropleura, a giant myriapod related to modern millipedes, reached lengths of up to 2.5 meters and widths of 50 centimeters. It is the largest known land invertebrate in Earth's history. It walked through the Carboniferous forests on dozens of legs, eating decaying plant matter, its enormous armored body moving through the undergrowth like a living tank. 2.5 meters long, a millipede the size of a car, walking through forests that already looked nothing like anything in the modern world. Alongside Arthropleura lived the scorpions, ancient scorpions, similar in basic body plan to their modern descendants, but in some cases reaching lengths of 70 centimeters, hunting through the leaf litter of the forest floor with their characteristic patience and their venomous stingers raised. And the spiders, ancient spider relatives, spinning webs between the trunks of the scale trees, hunting the enormous insects that moved through the Carboniferous air. The Carboniferous forest floor was a world of extraordinary invertebrate diversity and size. Every piece of fallen wood, every patch of moss, every shallow water channel was home to creatures that modern science is still working to fully understand from the fossils they left behind. And above the forest floor, in the air itself, something was happening for the first time in the history of life on Earth. Things were flying. The Carboniferous is the period when powered flight evolved for the first time in the history of life on Earth. Not gliding, not falling with style. Genuine, powered, flapping flight. And the creatures that achieved it first were not birds, not bats. They were insects. And the insects of the Carboniferous sky were unlike anything that has ever flown since. The Carboniferous world was not only forest. Much of the continental surface was covered by shallow warm seas, particularly during the earlier Mississippian subperiod, and those seas were alive with a richness and diversity that rivals anything in the modern ocean. The Carboniferous seas were dominated by creatures that have either disappeared entirely from the Earth or survive today only in drastically reduced numbers. The crinoids, sea lilies, covered the shallow sea floors in such numbers that their fossilized remains form entire layers of limestone rock, visible in cliff faces and quarries around the world today. They were not plants, despite their appearance. They were animals, relatives of starfish and sea urchins, anchoring themselves to the sea floor and extending their feathery arms to filter food particles from the water. In the Carboniferous seas, they grew in forests of their own, swaying in the underwater currents, their delicate stems and feathery crowns creating an underwater landscape as otherworldly as the forests on land. Among the crinoids moved the sharks. The Carboniferous was an extraordinary period for shark evolution. Modern sharks are remarkable animals, but the sharks of the Carboniferous were something else entirely. Evolution was experimenting with the shark body plan in ways that have never been repeated. Helicoprion, one of the most extraordinary marine animals of the late Carboniferous and early Permian, possessed a spiral whorl of teeth in its lower jaw that formed a structure like a circular saw blade. The whorl could contain over 180 individual teeth arranged in a tight spiral. Nothing quite like it has ever evolved before or since. Exactly how Helicoprion used this extraordinary dental arrangement is still debated by paleontologists today. A shark with a circular saw in its mouth, moving through warm Carboniferous seas among forests of sea lilies. The freshwater swamps and rivers of the Carboniferous were equally rich with life. Enormous lungfish, relatives of the modern lungfish that still survive in Africa, South America, and Australia, moved through the murky swamp waters. Ancient ray-finned fish darted through the shallows. And in the deeper river channels, the early ancestors of the great predatory fish lineages that would eventually produce the pike, the bass, and the freshwater giants of the modern world. The swamps themselves, the shallow, warm, vegetation-choked waterways that connected the coal forests, were the most biologically productive environments on the Carboniferous Earth. Every surface was covered in life. Every water body was full of it. The boundary between land and water was blurred by the density of vegetation growing in both. It was in these swamps that the amphibians spent their lives, hunting, breeding, laying eggs in shallow water, crossing the boundary between aquatic and terrestrial existence dozens of times a day. And it was from these same swamps that the first fully terrestrial reptiles, the ancestors of everything that would come after, were taking their first tentative steps away from the water. The swamp was both the cradle and the crossroads of Carboniferous life, and above it all, the air. The seas held their wonders, the swamps held their mysteries, but it is in the air of the Carboniferous that perhaps the most extraordinary story of this entire period plays out, because the air itself was different, fundamentally, physically, chemically different from the air we breathe today, and that difference changed everything. Take a breath. The air you just breathed is approximately 21% oxygen. It has been roughly this concentration for millions of years. Your body is exquisitely calibrated to function at this level. Too little oxygen and you lose consciousness. Too much and the oxygen itself becomes toxic, damaging your cells, causing seizures, eventually killing you. 21% is the number that life on Earth has settled on. In the Carboniferous, the number was different. During the peak of the Carboniferous period, approximately 300 million years ago, the oxygen concentration in the Earth's atmosphere reached approximately 35%, perhaps higher. Some estimates suggest it may have reached as high as 35%. 35% oxygen, 2/3 higher than today. The reason was the forests. The vast Carboniferous forests were photosynthesizing on a scale the Earth had never previously experienced. They were pulling carbon dioxide out of the atmosphere and releasing oxygen in quantities that changed the chemistry of the air itself. And because the dead wood was not being decomposed and releasing its carbon back, the oxygen just kept accumulating. The relationship between Carboniferous oxygen levels and the size of the period's animals is one of the most fascinating areas of current paleontological research. Higher oxygen levels allow arthropods, which breathe through passive diffusion systems rather than lungs, to grow much larger than they can in lower oxygen environments. The giant insects and myriapods of the Carboniferous may have been directly enabled by the extraordinary oxygen levels of the period. But the effects of 35% oxygen went beyond giant insects. Fire. In an atmosphere with 35% oxygen, fires burn differently than they do today. They ignite more easily. They burn hotter and faster. They spread with a ferocity that would be extraordinary to witness. The fossil record of the Carboniferous contains abundant evidence of ancient forest fires. Charcoal, fossilized as inertinite in coal seams, has been found throughout Carboniferous deposits around the world. These ancient fires were not rare events. They were a regular feature of the Carboniferous world. Lightning strikes in a 35% oxygen atmosphere would have ignited fires of extraordinary intensity. Fires that swept through the ancient forests with a speed and ferocity that dwarfs any modern wildfire. And yet, the forests persisted, grew, covered the continents, because the Carboniferous forests grew with a speed and abundance that could absorb even these catastrophic fires and continue. The land was so fertile, the climate so warm and wet, the biological imperative to grow so powerful that fires, even fires of Carboniferous intensity, were simply part of the cycle. Burn, regrow, burn again, regrow, and each cycle left another layer of charcoal and deadwood compressed into the swamp floor, building the coal, layer by layer, century by century, for 60 million years. The high oxygen atmosphere of the Carboniferous made the forests burn and the invertebrates grow large. But perhaps its most spectacular effect was on the insects, because in an oxygen-rich atmosphere, with abundant food and no predators capable of catching them, the insects of the Carboniferous achieved sizes that have never been equaled before or since in the history of life on Earth. The Carboniferous sky was busy. For the first time in the history of life on Earth, things were flying, not gliding from trees, not being carried by the wind, genuinely flying, beating their wings against the thick, oxygen-rich air and going where they chose. The first flying insects appeared in the Carboniferous, and they did not start small. Megafauna was a dragonfly, or rather, it was the Carboniferous equivalent of a dragonfly, a griffinfly, an insect with a body plan similar to the modern dragonfly, but vastly, extraordinarily larger. The wingspan of Megafauna reached 70 centimeters. Some specimens suggest wingspans approaching 1 meter, 70 centimeters from wingtip to wingtip, a flying insect the size of a modern crow, moving through the Carboniferous sky at speeds of up to 40 kilometers per hour, hunting other flying insects with the same predatory precision that its tiny modern relatives use today, its compound eyes giving it a nearly 360-degree field of view, its powerful legs extended in a basket formation to scoop prey from the air. Imagine standing in a Carboniferous forest and watching Megafauna patrol the tree canopy above you. The sound of its wings, the deep, buzzing hum of those enormous wing surfaces beating against the thick, ancient air. The flash of its wings catching the filtered forest light as it banks and turns between the scaled tree trunks. Megafauna was not alone in the Carboniferous sky. Megafauna was another giant flying insect, with a different wing structure, suggesting that flight evolved multiple times independently during the Carboniferous. Brodioptera, Stephanotypus, names that most people have never heard, belonging to creatures that dominated the Carboniferous sky for tens of millions of years and left descendants that still fill our summer evenings with the sound of wings. The giant size of Carboniferous flying insects has been directly linked to the high oxygen levels of the period by multiple scientific studies. Laboratory experiments with modern insects raised in high oxygen environments have produced measurably larger specimens. The oxygen hypothesis for Carboniferous insect gigantism is currently the most widely accepted explanation among paleontologists. On the ground, the situation was equally dramatic. Pulmonoscorpius, the lung scorpion, was a scorpion that reached lengths of 70 centimeters, a scorpion you could not step on and ignore, a scorpion that would have been a genuine and significant physical threat to the early amphibians and small reptiles sharing its environment. Megarachne, originally identified as a giant spider before later analysis revealed it to be a sea scorpion that had ventured into fresh water, reached sizes that make modern arachnophobes deeply uncomfortable to contemplate. Whether or not the largest Carboniferous arachnids were technically spiders, The Carboniferous forest floor contained spider relatives of sizes that have no modern equivalent. And the myriapods. We have already met Arthropleura, the 2.5-meter giant millipede. But Arthropleura was not alone. The Carboniferous forests contained multiple species of giant myriapods. Centipedes and millipedes of extraordinary size, moving through the ancient undergrowth in a world where their size was not remarkable, where it was simply what these animals were, a world of giant insects, giant scorpions, giant millipedes, giant dragonflies overhead, and beneath it all, the quiet, patient work of the forests, falling, sinking, becoming coal. The creatures of the Carboniferous were extraordinary, but everything they were, their size, their abundance, their extraordinary diversity, was made possible by the forests. And those forests were doing something that would shape the future of the planet in ways that their inhabitants could not possibly have known. They were building the coal that would one day power a civilization 300 million years in the future. There is a direct line between a lepidodendron tree falling into a Carboniferous swamp 300 million years ago and a steam engine running in Victorian England in 1850. It is not a metaphorical line. It is a literal physical connection. The carbon in the body of that ancient tree, the carbon that the tree built from atmospheric carbon dioxide through 300 million years of quiet burial, compression, and chemical transformation, is the same carbon that burned in the firebox of that steam engine. The same atoms, the same chemical bonds, broken apart by fire 300 million years after they were formed by photosynthesis. This is what coal is. Coal is time made solid, carbon made permanent. The Carboniferous forest made dense and dark and burnable. The process that created coal was gradual beyond human comprehension. A tree falls into a Carboniferous swamp. Because the decomposing bacteria have not yet evolved to break down lignin, the tough structural compound in wood. The tree does not rot. It sinks slowly into the swamp sediment. More trees fall on top of it. More sediment accumulates. Over thousands of years, the organic layer, now called peat, is buried deeper and deeper under the weight of what accumulates above it. Pressure builds, heat from the Earth's interior increases, water is squeezed out, the organic material is compressed, the molecular structure changes. Over millions of years, peat becomes lignite. Lignite becomes bituminous coal. Bituminous coal, under sufficient pressure and heat, becomes anthracite, the hardest, densest, most energy-rich form of coal. The vast majority of the world's coal deposits, approximately 90% of all coal on Earth, was formed during the Carboniferous period. The coal fields of Pennsylvania, West Virginia, the English Midlands, the Ruhr Valley in Germany, the Donbass in Ukraine, the coal fields of China, all of these were Carboniferous forests. All of these were once scale trees and giant ferns falling into ancient swamps. 90% of all the coal on Earth, formed in 60 million years of Carboniferous forest death. The Industrial Revolution, the transformation of human civilization that began in the late 18th century and created the modern world, was powered almost entirely by Carboniferous coal. The steam engines that drove factories, ships, and trains, the furnaces that smelted the iron and steel that built the infrastructure of modernity, the heating systems that made dense urban living possible in cold climates, all of it powered by ancient trees. We think of the Industrial Revolution as a human achievement, and it was. But it was also, in a very real sense, a gift from the Carboniferous, a 300 million year old gift of stored solar energy, preserved in the bodies of ancient forests, waiting for a species clever enough to dig it up and use it. We found it. We used it. And the carbon that the Carboniferous forests spent millions of years removing from the atmosphere, we have been putting back in the space of 200 years by burning their remains. The Carboniferous built the world, and we are slowly unbuilding what it built. The coal tells the story of what the Carboniferous left behind, but the Carboniferous itself did not end quietly. The great forests that had covered the land for 60 million years, the forests that produced the coal, the oxygen, the giant insects, and the ancient amphibians, came to an end, slowly, then suddenly, in a collapse that changed the earth as profoundly as the forests themselves had changed it when they arrived. Nothing lasts forever. Not empires, not civilizations, not species, and not the extraordinary conditions that made the Carboniferous possible. Around 307 million years ago, roughly in the middle of the Pennsylvanian subperiod, something began to change. The vast tropical coal swamp forests that had covered the equatorial regions of the assembling supercontinent for tens of millions of years began to fragment. The event is called the Carboniferous rainforest collapse, and it was, in its way, as dramatic as any mass extinction. The cause was climate. The great supercontinent of Pangaea was assembling with inexorable geological patience. As the landmasses came together, the ocean circulation patterns that had kept the equatorial regions warm and wet began to change. The interior of the assembling continent, far from the moderating influence of the ocean, became drier, seasonal, less reliably tropical. The coal swamp forest required consistency, warmth, perpetual moisture. They could not adapt to seasons. The forests fragmented. What had been a continuous carpet of ancient forests covering the equatorial regions broke apart into isolated islands of forest separated by drier, more open environments. The biological corridors that had allowed species to move freely across the forest landscape were severed. Populations became isolated. Evolution accelerated in the isolated fragments as different selective pressures in different environments drove different lineages in different directions. The Carboniferous rainforest collapse is now recognized by paleontologists as a significant driver of evolutionary diversification. The fragmentation of the great forests isolated populations of amphibians and early reptiles in separate forest fragments, promoting rapid speciation. The reptiles, better adapted to drier conditions than the amphibians, thrived in the new mosaic landscape. The amphibians were increasingly confined to the remaining wet areas. The collapse of the forests was not the end of life. It was paradoxically an acceleration of it. The reptiles that had been a minor component of the Carboniferous fauna, small, unobtrusive, overshadowed by the giant amphibians and the enormous arthropods, found themselves in a world that their biology was better suited to than any competitors. They spread into the drier environments. They diversified, they grew larger, they developed new strategies for survival. The giant arthropods suffered more. As oxygen levels began to fall from their Carboniferous peak, partly because the forests were fragmenting and producing less oxygen, partly because the decomposition of organic material was becoming more efficient as the bacteria and fungi evolved to break down lignin. The conditions that had enabled giant insect size began to disappear. Meganeura's descendants shrank. Arthropleura disappeared. The giant scorpions retreated to the margins. The world was becoming smaller, drier, more familiar. The Carboniferous was ending, and the Permian was beginning, a period that would end in the greatest catastrophe in the history of life on Earth. But that is a story for another night. The great forests fragmented, the giant insects shrank, the reptiles inherited a drying world, and beneath the feet of all these creatures, the coal accumulated, compressed, waiting with geological patience for a species that would not arrive for another 300 million years. The Carboniferous was over, but what it left behind was just beginning its long journey toward us. The Carboniferous ended 300 million years ago, and yet it is everywhere around us. It is in the coal seam, beneath the ground. It is in the power station that generates electricity. It is in the plastic made from petrochemicals. It is in the carbon dioxide dissolving into the oceans and accumulating in the atmosphere. The Carboniferous is not ancient history in the way that human civilizations are ancient history. It is present, active, consequential. Every piece of coal ever burned was a Carboniferous tree. Every carbon molecule released into the atmosphere by burning fossil fuels was captured from the atmosphere by a Carboniferous forest 300 million years ago. We are not just studying the Carboniferous when we study it. We are living with its consequences. But the Carboniferous also gave us something beyond coal. It gave us the reptile line, the small, unremarkable Hylonomus and its relatives, the first animals to fully conquer the land, were the ancestors of the dinosaurs, of the birds, of the mammals. The Carboniferous forests did not just produce the fuel of the Industrial Revolution. They produced the evolutionary conditions that eventually produced the species doing the burning. We are children of the Carboniferous in more ways than one. Lie quietly for a moment and think about what that means. 350 million years of history, 60 million years of extraordinary forest, giant dragonflies in oxygen-rich air, 2.5-meter millipedes on the forest floor, ancient swamps accumulating the carbon that would one day heat our homes, all of it leading through an unbroken chain of life and death and transformation to this moment, to you, breathing air that is 21% oxygen, resting in a world built on Carboniferous coal, descended from the first creatures that learned to live without the water. The ancient earth has spoken tonight, and what it told you across 300 million years of silence is that everything is connected, everything has a history, and the ground beneath your feet remembers things that no human has ever witnessed. Rest now. The world is very old and very beautiful. Sleep well.